All right, greetings, guys. I'm so sorry I could not be here today. Here are your notes for 3.3 complex numbers. Yes, we skipped 3.2, so do not worry. Deep dive right into imaginary numbers. Imaginary numbers, they occur when we want to take the square root of a negative number. So if we had x squared is equal to a negative 25, in order to solve, I would have to take the square root of both sides to get x by itself. But on the right-hand side, I have a negative number. Sure, it's a perfect square, but 5 times 5 does not give us a negative 25. And negative 5 times negative 5 does not give us a negative 25. So what happens? Well, given the square root of a negative a, that is the same thing as saying the square root of negative 1 times a, which is the same thing as saying the square root of negative 1 times the square root of a. Now, folks, the square root of negative 1, we're going to call that an I. I times the square root of a. So i's with different exponents. If we have I to the first power, well, folks, that's just I. If we have I to the second power, that's going to be a negative 1. So that would mean that I to the third power is equal to a negative I, because this breaks down to I squared times I, and I squared is a negative 1 times I. Remember, when you have the same base, keep the base and add your exponents, so 2 plus 1 is 3, so that's the breakdown for that guy. But we also know that I squared is a negative 1, so I'm going to replace a negative 1 for I squared, and negative 1 times I gives us that negative I. So I to the fourth power will break down to I squared times I squared. And we already established that I squared is negative 1. So plug it in, and you get a positive 1. All right. So when we take the square root of imaginary numbers, we're going to simplify those radicals by pulling out the negatives first. They get pulled out first, and we call them i's. So let's take a look. Suppose we look at this example, writing each as an imaginary number. This is the square root of negative 6. I'm going to pull out that negative, call it an I, and I'm left with 6 as my radicand. The number under the radical is called a radicand. The number under the radical is called a radicand. This is called a radical symbol, radical sign. And then whatever number is here in the index, there's an invisible 2 there, you just don't see it. That's called the index, okay? Part B. The square root of negative 9. Pull out that negative first, call it an I. You have square root of 9 in your radicand, but the square root of 9 is 3. So your final solution is 3 times I. Okay. Let's go ahead and simplify these guys. Break these guys down into the product of your largest perfect square times another number. But first, always pull out the negative and call it an I. So I'm going to break down 125, that's 25 times 5. And the square root of 25 happens to be 5, so I'm going to pull him out. Bring down your I. And then this guy stays in the radicand, in the doghouse. 5i times radical 5. Number 2. Now, if I'm going too fast, please feel free to pause, rewind. That's the beauty of these videos. Call it an I, You're taking the square root of 12. 12 breaks down into 4 times 3. 4 is the largest perfect square that fits into 12. Square root of 4 is 2, so pull him out. So you're looking at 2i on the outside times radical 3 on the inside. 3 stays in the doghouse. You can't take the square root of 3 evenly. Number 3, 2 times the square root of negative 10. Pull out the negative. That becomes a 2i times radical 10. 10 cannot be broken down into anything more than just 2 times 5. So we're just going to leave it alone. There's no perfect square in 10. Let's take a look at number 4. Okay, before you multiply your radicands, you must make sure you pull out the negative and call it an I. So I times radical 4 times I times radical 25. Folks, you're going to take your outside values and multiply them. You get I squared. Your inside values, you can multiply them. 4 quarters, 4 times 25 cents is 100. Okay. Now, we have a few things to do. The square root of 100 is 10, yes. But I squared is equivalent to a negative 1. So negative 1 times 10, so your final answer is negative 10. The I is dropped. It's dropped because you replaced it with a negative 1. You replaced I squared with a negative 1. Okay, take a look at number 5. This is read as 2 times the square root of negative 15 times the square root of negative 3. First step, pull out that negative, so you're looking at a 2i times the square root of, I'm going to break this down to 5 times 3. And then over here, I'm going to pull out, there's a times, I'm going to pull out an I times radical 3. So once again, folks, take your outside numbers, multiply them, that becomes 2i squared. Take the numbers in the radicand. Take your radicand and multiply them together. So you've got 5 times 3 times 3. So you've got a pair here. 3 times 3 is 9. Square root of 9 is 3. So just pull him out. So you've got 2i squared times 3 times radical 5 as your radicand. So now simplify this even further. I'm going to continue this problem up here. You have 2i squared, but I squared is a negative 1, times 3 times radical 5. So these outside numbers become a negative 6. Bring down your radical 5, and there you have it. Negative 6 times radical 5. Take a look at number 6. This one's easy peasy lemon squeezy. Your squares cancel out your square roots. Your answer is negative 10. That's it. Complex numbers. Complex numbers are when you take a real number and combine it with an imaginary number. There's a standard form for it. That standard form is your real number plus or minus, because it could be minus, your imaginary number. So that's why I have that there. You must know this standard form. Don't forget it. So complex numbers, what are they? They can be real numbers with imaginary numbers. You can either add them, subtract them, you can even multiply and divide them, which is what we're going to look at now. Adding and subtracting complex numbers. When we look at number 7, we are adding, so you're going to go ahead and rewrite your entire expression without parentheses. So you have 2 minus 3i, distribute your addition sign, plus 7 plus 4i. Now at this point, you just need to combine like terms. Positive 2 plus 7 gives you a positive 9. And then you have a negative 3i plus 4i. Always take the sign in front. That's plus 1i, or just I. So 9 plus I is your solution. Combine like terms and notice how this is in A plus BI format, where 1 is your B, 9 is your A. Take a look at number 8. Again, we're going to rewrite this entire expression without parentheses. Make sure you distribute this negative sign. It is subtraction, but you are distributing. Becomes a minus 3 plus I. Combine like terms. Positive 6 minus 3 is 3. Negative 5i plus 1i is a negative 4i. Multiplying complex numbers. So the thing you need to understand here is that if I is equal to the square root of negative 1, you pull this out and call it an I, then that means if you were to take the square of both sides, well then I squared is equal to negative 1. So you must remember that I squared is equal to negative 1. With that, let's take a look. Multiplying. You guys remember FOIL. First, outer, inner, last. So first, multiply it. That's a positive 28. Outer, negative 7 plus I. That's a negative 7 times a positive I. That's a negative 7i. Remember, you're multiplying. And then you have the inner, negative I times a negative 4. That's a positive 4i. And then your last, negative I times a positive I is a negative I squared. Now remember, we just got done saying that I squared is a negative 1, so we have to be careful to plug in a negative 1 for I squared. Combine like terms, folks. When you combine like terms, bring down your 28. This becomes a minus 3i. Minus, okay, but I squared is a negative 1. Look at what I did. I put negative 1 in parentheses. So now when I go to combine like terms, this becomes a plus. So you have 28 minus 3i plus 1. That is 28 plus 1, which is 29. 28 plus 1, that's 29, minus 3i. It must always be written in the A minus BI format, or plus BI. In this case, it's minus. So this becomes your final solution. Take a look at number 10. Number 10 is kind of a trick question. This is actually meant to be read as 7 plus 6i times itself, 7 plus 6i. Use the FOIL method. So first, 7 times 7 is 49. Outer, 7 times positive 6i is a positive 42i. Inner, again, positive 6i times a positive 7 is a positive 42i. And then last, positive 6i times positive 6i is positive 36i squared. So let's go ahead and combine like terms. We have 49, bring it down, plus 84i. These are like terms. And then bring down your plus 36, but instead of I squared, I need you to plug in a negative 1, because I squared is negative 1. Okay, let's simplify even further. We have 49 plus 84i minus 36. So we are looking at positive 49 minus 36 gives me a 13 plus my imaginary portion, 84i. And this becomes my final solution for number 10. take a look at number 11. Again, FOIL method, but I'm going to teach you a shortcut here. Same, same, so just multiply them, positive 9. Same, same, so just multiply them, 16i squared. These two guys need to be opposite, and they are. You have one subtraction, one addition. Negative times a positive is a negative. So you have a 9 minus 16i squared. Plug in a negative 1 for I squared, and you have 9 minus 16 times a negative 1. That's 9 plus 16, which is 25. So in this case, you only have a real answer, a real number. There is no imaginary to it. Now, folks, this shortcut method only works because one is a subtraction, the other is addition. You can have same, 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 but your signs must be opposite to do the shortcut method. Okay, take a look at conjugate. Now, conjugate, folks, the thing you need to know about conjugate is that the only thing that changes are the signs on the imaginary part. So your BI is the imaginary part. If it's a positive, it's now going to be a negative when you apply the conjugate. Same thing here. You apply the conjugate. If it's a minus BI, it's going to become a plus BI. And notice A is always positive. If you start with a positive real number, then you're going to end up with a positive real number. If you started with a negative real number, then your conjugate is going to be negative A plus BI. Or negative A plus BI, then that's going to be negative A minus BI. So your A's, if you start with this, you end with that. The only thing that changes are these guys. Okay, with that in mind, let's state the conjugate here. Here your conjugate is a positive 2i. Number 13, your conjugate is a negative 3 minus 5i. And for number 14, your conjugate is a negative 4i. Okay, so we talked about adding, subtracting, and multiplying with imaginary numbers. Now we're going to talk about dividing. So much like simplifying radicals, if you have a radical in the denominator of a fraction, then you have to rationalize the denominator by multiplying that radical to both numerator and denominator. Same idea with imaginary numbers. You're going to have to multiply the conjugate to remove I from the denominator. So here we go. This is similar to rationalizing the denominator with radicals, only this time we're going to multiply by its conjugate. There is no A value, no real number, so don't worry about it. So at the top, you're left with a negative 6i. On the bottom, you're left with a negative 9i squared. Well, these negatives will cancel because negative divided by negative is a positive. And then you're looking at 6i divided by 9 times a negative 1, because remember, I squared is a negative 1. So 6i divided by a negative 9, reduce your fraction. And you should get, reduce it by 3, you get negative 2i over 3. And there's no more imaginary number in the denominator, which is what we wanted. Take a look at 16. Here we go. Multiply by the conjugate. The conjugate is 2 plus 4i. Notice the 2 stays positive. It's positive here. It stays positive there. Don't change the sign on your real number. What you do to bottom, you must do to the top as well. Here we go. Apply the distributive property. You have a 6i plus 12i squared. Take care of your math. Over here, remember what I taught you. Same, 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 opposite. So use a shortcut method. 2 times 2 is 4. And then 4i times 4i, negative 4i, well, just 4i times 4i is a 16i squared. And then a negative times a positive gives me a negative. So when I go to simplify, I have the following. 6i plus 12 times a negative 1, because I'm replacing this guy with a negative 1, divided by 4 minus 16 times negative 1. And once again, I'm replacing this guy with a negative 1 because I squared is negative 1. So simplifying this even further, we're looking at 6i minus 12 divided by 4 plus 16, because negative times a negative is a positive, and 4 plus 16, hey, that's 20. So once again, we're looking at 6i minus 12 all over 20. But we can't leave our answer like that. Let's go ahead and factor from the numerator. Choose a different color. Let's choose blue. If I factor out the GCF from the numerator, I get 6 times I minus 2 all over 20. Now I can reduce my fraction here by 2. I would get a 3 and a 10. But I have some things I need to take care of. Remember, we talked about a plus or minus bi, standard form, right? Standard form. So I need to get this fraction in standard form. Let's do it. My final answer would be 3 times a negative 2, because the sign on 2 is negative, plus I, because the sign on I is positive, all over 10. So take care, make sure you do that for all of your solutions. If you do not, I take points off. Okay. One more problem. This one's easy peasy lemon squeezy, not stressy messy lemon zesty. Equate complex fractions. So for 17, you have to find the values of x and y that make this statement true. So you've got 5x minus 7 plus y plus 4 times I equals 13 plus 11i. So you have to find out what x and y are to make that statement true. So here's what you're going to do. You're going to set the real parts equal to each other and set the imaginary parts equal to each other. So here are your real parts. Your 5x minus 7, your 13. So 5x minus 7, I'm going to set that equal to 13. This addition sign and this addition sign separate our terms. Remember, addition and subtraction signs separate our terms. So the second term we're looking at is y plus 4 times I. So y plus 4 in parentheses times I is equal to this portion. And actually, I want to take the sign in front of it, is equal to a positive 11i. So now I've got my two equations, the real one and the imaginary one. Let's go ahead and solve the real one. Add 7 to both sides. 5x is equal to 20. Divide both sides by 5 to solve for x, and x is equal to 4. Awesome. Because now step 2 says to solve for both equations. After you set the real parts equal to each other and then the imaginary parts equal to each other, you can solve for both the solutions. Let's take care of the imaginary part. I've got I being multiplied to this whole thing. And I've got I being multiplied to 11 on the other side. Why don't I just go ahead and divide both sides by I? That way, they're forced to cancel out. I don't want to deal with I don't want to deal with imaginary things. I want a real solution. So I'm left with y plus 4 on the left, 11 on the right, subtract 4 from both sides, and y is equal to 7. And boom shakalaka, Bob's your uncle. All done. Now you guys will have enough information you need to complete today's classwork. Use your notes. Reference your notes. Go back and review this video if you need to. All right, I'll see you guys later. Bye.